Now that we've talked about balancing chemical equations and what solubility is, we can work on looking at precipitation reactions. These are reactions that form a solid from aqueous solutions. And this is what happens with laundry detergent and magnesium and calcium ions in hard water. The precipitate is the solid, and this reminds me of precipitation is a term that meteorologists use. The weatherman talks about precipitation, right? And snow, sleet, rain, hail, these are all precipitates, right? There's something that falls out of the sky. And if you look at a lot of precipitation reactions, it looks like it's snowing almost. And you've got something falling down. And so that's the precipitate, is the solid that forms. Here's an example. A potassium iodide solution, which is colorless, and a lead nitrate solution, which is also colorless. And you mix them together and you get this brilliant blue. That's not blue, it's yellow. I am not colorblind, although some of my children are. Brilliant yellow precipitate forming. This is not just a color change. If you look at the solution, we can see through this one. It's clear. You can see through it. It's transparent. And this part, we would say that's cloudy. It's opaque. You can't see through it. The reason you can't see through it is that those are larger particles. They're still very small particles. They're not like big boulders or something. They're small particles, but they're large enough that they block the light. And so you can't see through it. So anytime you get this opaque or milky appearance, you've got a solid formed. Sometimes you can't see that it's a solid until you let the test tube or the container sit for a while. And the solid will gradually settle to the bottom and you'll see this layer of solid at the bottom. But anytime it gets cloudy like that, we know that a precipitate has occurred. Precipitation reactions do not always occur if you mix two aqueous solutions. Here we've got potassium iodide and sodium chloride. These are two ionic solutions, aqueous. We pour them together, nothing happens. There is no reaction. There's no precipitate that forms. Well, we can predict whether a precipitation reaction will happen or not by using the solubility rules. You're only going to get a precipitation reaction if you've got insoluble compounds that are going to be formed. So what happens in a precipitation reaction is you've got two solutions that contain soluble compounds, you mix them together, and you form an insoluble compound, and that's what is precipitating. So let's look at what happens when potassium iodide and lead nitrate are mixed with pictures. So here's the before. You've got potassium ions and iodide ions. And if we look potassium iodide up in the rules of solubility, we'd see that it's soluble. And over here we've got lead nitrate. And according to the solubility rules, that's also soluble. Here, this formula is PbNO3 And so for every lead 2+ ion, we're going to have 2 nitrate ions floating around. These are all soluble and they're going to mix. Immediately after mixing, what we have are these different ions together. But what are the different possible combinations for these ions? I can't remember. Okay, I was supposed to draw something. I was pretty sure I was supposed to draw something, but I couldn't remember. Well, we can make a table, and so we've got potassium ions and we've got lead 2+ ions. And for the anions, we've got iodide and we've got nitrate. Not. So there's a possibility for 4 different compounds. We can combine the potassium with the iodide. We'll get Ki. We can combine the potassium with the nitrate. We can combine the lead 2+ with the iodide. or we can combine it with the nitrate. Now, even without looking at a solubility rules table, there are two of these that we can eliminate as the possible solid that's formed. What do we know about the solubility of Ki, just from what's told to us? It dissolves, right? It's aqueous. Ki dissolves. That's one of the starting things. That's not our precipitate. The lead nitrate also dissolved. It was dissolved in the beaker. That's not the precipitate. Oops, trying to X off the wrong place. So that leaves these two guys as the possibilities for that bright yellow precipitate that's formed. We can go to the table of solubility rules, and we see that potassium compounds are always soluble, nitrate compounds are always soluble. This is soluble. It's not an insoluble compound. If we look up this one, we don't see lead listed, but we see iodide. Iodides are generally soluble except with Pb2+, and that's what we have here. So this is the thing that's forming the precipitate. So what happens as these guys mix around is that when the lead ion runs into the iodide ions, they're very attracted to each other, and they're going to form a solid, and they're not going to mix. So I have this imaginary land that I decided to call Chemistry Land. It's a little bit like Disneyland. Disneyland's the happiest place on Earth, and you may not agree that Chemistry Land is the happiest place on Earth, but we're going to go on a little trip to Chemistry Land. So in Chemistry Land, I think of the metals as being like guys, they're masculine, and the nonmetals, the negative ions, as being non-masculine or feminine. And so what happens with a situation like this is we've got two guys and two girls that have gone to a party, and the beaker is the party. Okay, so potassium and iodide came to this party together, and lead and nitrate came to the party together. And here they've just gotten there, and they're all mingling around. And then what's going to happen? Well, the potassium runs into the nitrate, and they have a little chat, but there's no big attraction. There's no chemistry there. And so they just keep mingling. But when lead gets an eye of iodide, he's like, oh my goodness. And these guys just, sparks flying. There's chemistry between these two, okay? These guys are not going to mingle anymore. They're going to be together the rest of the night. In fact, they might find a couch on the back porch, and they're sitting out there making out, right? They're not mingling. They are a precipitate. They're a lump at the bottom of the beaker, because these two get together and they form a solid, and they do not mingle because they just like each other so much. Okay? So that's what happens. The potassium and the nitrate ions, they're just mingling. They're not particularly bummed or anything. They weren't that attached to the people they came with. They just came to have fun at this party. I'll be referring back to that again. So here's lead and iodide making out on the couch, right? And here are the other guys. They're mingling around. They're enjoying the party. So what happens is the lead iodide precipitates. How do we predict that? We look at the possible combinations. We say, okay, well, these people came to a party. What are the possible combinations for these guys to get together? Let's see if any of them are insoluble compounds. If they're insoluble compounds, you get a precipitate. So we're going to learn how to write equations for precipitation reactions. We can actually predict what the products are. So the first thing we need to do is write the formulas for the two compounds as reactants in the chemical formula. And then we're going to make some little notes to ourselves. Below the equation, we're going to write the formulas of the ions with the charges, because this is going to help us out. Then we're going to try having these people swap partners. Okay, guy A came with girl B. Well, let's see if he likes girl D that came with guy C. Yeah, I didn't follow that either. Anyway, you get the idea. Swapping partners. just to see what happens. So you exchange the anions, and you write the formulas for those ions below, and then you go look in the solubility rules and see, are these guys going to be attracted to each other? Is there going to be this chemistry that causes this compound to be insoluble? These people will not mingle anymore. If both pairs are soluble, then there's no reaction. All that's happened is you've mixed things. That's no reaction. You can write no reaction next to the arrow. I'll even let you abbreviate that and say NR, N period, R period. That's chemistry for no reaction. Done. You don't have to do anymore. If there's a reaction, though, then you need to write the formulas for the compounds after the arrow, put AQ for the soluble product, and S on the insoluble product. Now, don't get S mixed up with soluble. It's kind of unfortunate that soluble and solid both start with an S. S is the state. It's a solid. Okay. And then balance the equation. Don't change the subscripts. Let's do some examples. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel 2 bromide are mixed. Well, we need some chemical formulas first. Since they didn't give us anything but the names, I'm going to start off on the second line. I'm going to write the ions with their formulas first. So potassium and hydroxide. Potassium is K, and we know from its position in the periodic table that it has a charge of what? +1. Hydroxide, do you remember what that one is? OH, and what's the charge? -1. Okay, so that's one couple. So here we got the guy and the girl. And then we've got nickel 2. So nickel is Ni, and the Roman numeral tells us it's 2+. Bromide is from bromine, and what's the charge on bromide? -1. So just a review on that, we look at the periodic table, we find bromine, he's in group 7A, sorry. And so you start with the noble gases on the right, that column is 0, and you count to the left, bromine's -1. So we've got these ion formulas written out with their charges. We need the charges so that we know how to combine them. Here we've got +1 and -1. We just need one of each. And so up here we're going to put KOH, and it says solutions of. This is aqueous. Plus, and here I've got Ni2+ and bromide. These charges are not the same. We can do the crisscross thing. Okay, if you are still not sure what I'm doing when I'm making these formulas, please talk to me. I can help you with that. This is not something that's going to go away. It's going to come back and bite you over and over and over again. So you need to figure this out. And I can tell from the worksheets that some of you are more than confused about it, which is understandable, but let's fix it. So we're going to do the crisscross thing, and I'll end up with NiBr2. And it says it's a solution, so that's also aqueous. And then we'll have the arrow. And this is where the swapping partners comes in. So I'm going to try nickel with hydroxide and see how they hit it off. And I'm going to try potassium and bromide and see how things go with them. So I'm just going to rewrite them over here. It doesn't matter which pair you put first, but it's always the guy and then the girl, the plus and then the minus. So K+, we'll try that with Br-, and then we'll take the other pair, Ni2+, and OH-. By writing the formulas for the ions with their charges next to each other, I can more easily see how to write the correct compound formula. And remember that in the formula for the compound, there are no charges showing. We don't see any charges in here. They clutter things up, so we don't show them. We only show charges when we're looking at individual ions. So K plus and Br minus, plus 1, minus 1, we need one of each. KBr. I'm going to leave a space for the state symbol. Ni, 2 plus, and OH. I'm going to need two of these. Because that's a polyatomic ion and I've got two of them, I need parentheses. And then I'll need a state symbol. Any questions yet? Now we need to go to the solubility rules. We look up potassium bromide. Potassium compounds are always soluble. So that one's aqueous. And then if we look at hydroxide compounds are generally insoluble, except, and it gives a couple of exceptions, nickel isn't one of them, is it? So this is our solid. Turns out nickel and hydroxide have a thing for each other. So we've identified that a precipitation reaction does occur. And now we need to balance it. This is a polyatomic ion. In a solution, the polyatomic ion stays together. The O and the H stay together. They were together here, they're together over there. And what that means is you can balance it as a unit if you would like. You can always take care of them separately, but you don't have to. So I'm going to balance them as a unit. And I'm just going to start on the left and see how things go. So here I've got one potassium, and there's no K's anywhere else. So one on the left and one on the right. And here I've got OH. I'm going to think of that as a unit. I've got one OH over there, and how many OHs over here? 2. So that means I'm going to put a 2 in front of KOH. That gives me 2 hydroxides. So I've got 2 hydroxides on the left, 2 on the right. But that messed up the potassium, didn't it? Because now I have 2 potassiums, and I've only got 1 over here. So I need to put a 2 here to take care of the potassium. Any questions? Once you see how this works, it's not that hard. It's just getting to that point can be pretty confusing. Now nickel. I've got 1 nickel here and 1 nickel there, so that's good. I've got 2 bromines and 2 bromines. So there's my balanced chemical equation for this precipitation reaction. Any questions?
How do you know how to pair like the K?
How do we know how to pair them up? Okay, so they come plus and minus, plus and minus. So this is a party that's happening in Reedley. Reedley's a small town, and it's like jumping 20 years back in time. This is not a party in San Francisco. Okay? So it's plus and minus, plus and minus. Nickel and potassium are not going to go off together. That might happen in San Francisco, maybe even in Fresno, and that's fine, but it doesn't happen in chemistry land. It's opposites attract. So you have to have a positive charge and a negative charge, right? Because 2 positives are going to repel each other. They're not going to form a compound. So these guys came in like this. There's only one other possibility, and that's if you swap partners. So you can think of it as switching the anions, if you want to think of it that way. I tend to draw these lines, and I put these 2 guys together. They're on the inside, and these 2 on the outside, and I rewrite them over here. But you're just swapping partners. Any other questions? Yes? Mm-hmm. This is an S on the far right. We got to get that adjusted one of these days.
How do you know which one to start with again for balancing?
For balancing, a lot of times it doesn't really matter. I tend to just start with the first element. And usually that works fine. Just remember, if you start going in circles, like we went in one circle here. We looked at the potassiums and they were fine, and then we went to the hydroxides and they weren't fine. So I put a 2 here and that changed the potassium. Then if I go over here and I start going and changing things over and over again, that's what I call going in circles. And then it's time to just stop. Start over, just copy your equation down somewhere else and start over and start with something else. Because for some equations, it doesn't matter at all what you start with. For other equations, there's one that if you start with that one, you're going to have a terrible time. And there's no hard and fast way to predict what that is. So if things start going badly, start over with somebody else. Any other questions? Yes? No? Just shaking. Okay, let's do another one. Write an equation for the precipitation reaction that occurs, if any, when solutions of ammonium chloride and iron 3 nitrate are mixed. And by the way, on the exam over this material, I will not, this question is combining nomenclature with balancing reactions and writing precipitation reactions. Okay, it's combining multiple skills. It's great in lecture, it's great as homework because it gives you some review from the other stuff. On an exam, I would give you the formula for the reactants and ask you to predict the products in balance. I wouldn't expect you to write the compound formulas from their names, just so you know. So ammonium chloride, what's the formula for ammonium ion? NH4 plus. And chloride is Cl minus. And then we have iron 3. Iron 3 is Fe3 plus. And then nitrate is one of those polyatomic ions, NO3 with a -1 charge. So putting these two guys together, ammonium and chloride, I've got +1 and -1, so I can just shove them together and their charges will add up to 0 and everything will be great. And that would be aqueous. We can assume that from it saying solutions of, but you could also look in the solubility rules and see that ammonium compounds are always soluble. And then we have iron nitrate. Here we've got a +3 and a -1. Do the crisscross thing, and we're going to get Fe, and we need 3 nitrates. I saw a lot of interesting things in the nomenclature worksheet. Use the parentheses only around polyatomic ions, and only when you have more than one. I saw, a couple of things like this, which that's really unfortunate because that's just not at all the same thing. So we do have to be careful with this stuff. And that's also aqueous. Now we're going to swap partners. Let's get rid of that. So I'm going to see if ammonium and nitrate are going to hit it off, and iron and chloride. It's always the cation and the anion. So over here, I'm going to write NH4 plus with his new partner. You could think of them as being at a dance and somebody's cutting in. They're swapping dance partners. And then I've got Fe3 plus and Cl minus. So I've got these two guys and these three guys. These three guys, not two. Charges do matter. You want to keep the charges the same. So this is NH4 plus, this is NH4 plus. This is Fe3 plus, that's Fe3 plus.
What about the 3 plus and the 1 negative for Cl?
We will take care of this imbalance when we write the formula. So this is -1 and that's +1. And that's not a problem because we can just pull in more chlorines and it'll be fine. And then we'll take care of all of that when you balance it. So on the last one, I went ahead and wrote the formulas for the products. But sometimes it is no reaction. So before we do that, let's see. Is ammonium and nitrate going to be soluble or insoluble? It's going to be soluble. Ammonium compounds are always soluble, and so are nitrate compounds. So this one's soluble, so I'm just going to write AQ there. And what about FeCl3? Does anybody have the table of solubilities? Chloride compounds are generally soluble except it's lead and silver and mercury. Is this one of the exceptions? No. So that's also a soluble compound. So we're done. These are always fun because there's less work. No reaction. They went to the party, they mingled, they met each other, they went home. Nothing happened. No reaction. Any questions? Then you don't have to balance it, you don't have to predict the products because there aren't any.
So if a solid was created, then there would be.
If one of these is an insoluble compound, then you have to finish it off.
So then you would have to balance it.
And balance it and do all that stuff. Yeah. And most of the time on homework or exams, that's what's going to happen. Most of the time. But every once in a while, no reaction. Here's another one. Potassium sulfate and strontium nitrate. So potassium, K+. Get that from the periodic table. It's in group 1. It's got a +1 charge. Sulfate, we memorize that. It's SO4, 2-. And then strontium is SR. And strontium is in group 2. So it's got a 2+ charge. And nitrate, we just looked at nitrate, NO3 with a -1 charge. So when we put these two guys together, we've got +1 and -2. Those are not the same. When we put the ions together, their charges have to add up to 0. They have to balance because ionic compounds are neutral. So we can do the crisscross thing, and we're going to have 2 of these and 1 of those. So K2SO4. The K does not need parentheses because it's just a single element. And the sulfate doesn't need parentheses. It's a polyatomic ion, but there's only 1, so it's not confusing. And here we've got strontium and nitrate. Strontium's 2+, nitrate's -1. Again, they're not equal, and so we're going to need 2 of these guys to equal the charge on that one. So we're going to get SR, and in parentheses, NO3, 2. You need to be careful that you make your capital letters big and your lowercase letters small. And with letters that have different shapes as capitals and lowercase, like this, I don't care how big it is, that's a lowercase n. And I don't care how small this is, some people want to do tin like that. That's a capital N. You can do that in the rest of your writing, but when you're writing chemical symbols, we have to get the size right, and we have to get the shape of the letter. You can't just use small caps. I saw some of that in the worksheet. So those are our reactants, and then we're going to swap partners. Try out strontium with sulfate and potassium with nitrate. So potassium and nitrate, strontium and sulfate. We go to the table of solubility rules. We find potassium at the top of the list, soluble. So this guy's going to be soluble. We look at the sulfate compounds, and what does it say about them? I know some of you have the book open. Is strontium one of the exceptions? No? So they're soluble, and strontium is not one of the exceptions. And this is another one like that. We were really hoping that that would be aqueous, but it turns out it isn't. On closer examination, that one's a solid. So now we need to finish this. So these two guys, +1, -1, shove them together. And I'm running out of room, sadly. That's aqueous. Wait a minute. I don't know why I put that in there. We do not want charges. And then strontium and sulfate, +2, -2, we're just going to shove those together as well. And I've run out of space, so I'm going to clear this out down here. And go plus SR, SO4, solid. Now we need to balance. So potassium, there's 2 of them. Over here there's only 1. So if I put a 2 in front of KNO3, that gives me 2 potassiums. Over here I've got SO4. That acts as a unit. It stays together. And over here I've got 1 SO4, so that's okay. Here I've got strontium, SR, 1 of them, and over here 1 SR. Here I've got 2 nitrate ions, and over here I've got 2 nitrate ions. These precipitation reactions are usually pretty straightforward to balance. Any questions? In a precipitation reaction, it's important to include state symbols because we want to know which one of these is the solid. It's possible that they could both be solids, but that's pretty unusual.